Hello again, everybody. I'm here to bring you a proof of Theorem 4.2. The setup is G is a group, A is some element of G, the order of A is equal to n, and K is some positive integer. In that case, then we have the following two things. The cyclic group generated by A to the K is the same as the cyclic group generated by A to the greatest common divisor of A and K, and the order of the element A to the K is n divided by the GCD of n and K. So I want to prove part 1 here. In order to prove part 1, we're going to want to show set equality. So we're going to want to first show that A to the K is contained in A to the GCD of n comma K. Alright, the way that I'll show that is I'll actually show that A to the K is an element of A to the GCD of nk. And that will be enough. If A to the K is in that, then certainly all of the powers of A to the K need to be in there, since the cyclic subgroup A to the GCD of nk needs to be closed. Alright, so on the next page we're going to have, let's let D represent the GCD of n and k. So in particular, this means that D divides K, so we can write K as D times something, so maybe D times R. So here R is some integer. So since A to the K is equal to A to the dr is equal to A to the d to the r, we have A to the K is a subset of A to the d. So I basically showed that A to the K is some power of A to the d. Alright, now by theorem 0.2, which you might remember as the GCD theorem, we can find integers such that we may write D as n times s plus k times t. So here I guess s and t are new integers that we're introducing here. Okay, so now my goal is to show the reverse containment. That is, that A to the D is a subset of A to the K. And much like we did before, I'll go one step further. I'll show that A to the D is an honest-to-God element of A to the K. So then, of course, all of the powers of A to the D need to be in that subgroup because, well, a group is closed. Alright, so notice that I can write A to the D as equal to A to the ns plus kt, and that this is equal to A to the ns times A to the kt, and this is equal to A to the n to the s times A to the k to the t. N is the order of A, so this is equal to the identity to the s times A to the k to the t, which is just equal to the identity times A to the k to the t, or just a to the k to the t? So we've done it. We've shown that a to the d is a power of a to the k. So this is an element of the cyclic group generated by a to the k. All right, good. So we now know that the cyclic group generated by a to the k is the same thing as the cyclic group generated by a to the d, where d is the GCD of n and k. So that GCD theorem came back to help us.